Alrighty, let's have some fun with net ionic equations. So, with net ionic equations, here's what we need to remember. We need to remember this idea of something called being soluble. Another term you might think of this is something called dissociation. Now, my spelling might not be great, but dissociation. When things are soluble or they dissociate, they do what we call, they break apart. Now, what do they break apart into? Well, we call this net ionic equations for a reason. And what's going to end up happening is when these things break apart, they're going to break down into what we call these things known as ions, meaning charged particles. Okay, so for solubility, in order for things to break apart, they have to have something to break apart in. And so when we have something that is breaking them apart or dissolving them, that substance is 99% of the time water. So we have a term for that, and that term is something called aqueous. What does that mean? It means the substance is dissolved in HOH, water, aqueous. So, if something says it's a solid, a liquid, or a gas, which I'm symbolizing with an S for solid, an L for liquid, or a G, it means it does not dissociate. It's not soluble. Now, for our purposes, what does that mean? It means it doesn't break apart. So if you remember with that double replacement reaction stuff, when we said things weren't soluble or didn't break apart, the reaction didn't occur, right? And that's because they couldn't break apart so that they could rearrange to make new substances, thus having a chemical reaction. So I'm going to do an example of a net ionic equation, and the equation is this. K3PO4, potassium phosphate, and it is aqueous, meaning it's dissolved in water. Reacts with 3HNO3. Pop quiz, hopefully you know, that is nitric acid. There we have an arrow. It's also aqueous, so it's dissolved in water. Creates H3PO4 as a liquid. Thus the L in parentheses, and 3KNO3, potassium nitrate, aqueous. So, this is the most important thing in net ionic equations. Things that are aqueous do dissolve. What does that mean? They break up into their individual ions. Things that are not dissolved in water, solids, liquids, and gases, do not dissociate. They do not break apart. So the only thing that does not dissociate is this thing right here, H3PO4. So here's what we do. We break it apart. K3PO4. Well, what this really means, K3PO4, is that you have a plus 1, and a plus 1 potassium, right? So what this breaks down into, K3PO4, is it'll break down into 3 K plus aqueous ions. Okay? Because there are 3 of them right there. PO4, there's only one of them. If there's more, there would have been a parentheses and a number. So that breaks down into 3 K pluses and, that's what a plus sign always means, 1 PO4. Now it's an ion right now because it's not bonded to these potassiums. Therefore, its charge is -3, and it's still aqueous. Plus HNO3. And there are 3 of them, so that's going to distribute. So here we go. What you end up getting here when this breaks apart is you have a plus 1 hydrogen and a -1 nitrate, right? And you have 3 of each. So what that does is breaks down into 3 H plus aqueous ions and 3 NO3 minus aqueous ions. Arrow. Okay, so that broke down into 3 of those and 3 of those. This doesn't break apart, so you just write it. H3PO4 is a liquid. It doesn't do anything. It doesn't break into ions. Plus this 3 distributes. So plus 1 minus 1. So you end up with 3K plus aqueous ions and 3NO3 minus aqueous ions. So that's what that breaks down into. Why? Because it was aqueous, and aqueous things dissolve. They break down. They're soluble. So what we end up doing now is the last thing. We have to look for participants in the game and people that are just watching. Now, in chemistry, we give that a name very similar to what you might see out in the real world, right? The people that are in the stands watching the game are not actually playing, right? We call those people spectators. Well, we do the same thing here. So we find the arrow, and our arrow is right here. And we look for anything that's on the reactant side, right, that matches exactly to the product side. Well, when we go to look, I see 3K plus aqueous ions here and 3K plus aqueous ions. Those are the exact same 3K plus ions. So you cross them off. They're spectating. They didn't actually do anything at all. They just stayed. Also, 3NO3 minus 1 aqueous ions and 3NO3 minus 1 aqueous ions there. When I look at this, there is nothing else that matches. Last part of a net ionic equation is then the net. Okay, so if somebody asks you what your net worth is, it's like all the things you own, all the money you have, all put together, right? Your net. Well, here is, okay, what's left over? Well, there's 1 PO4 negative 3 aqueous ion plus 3 H plus aqueous ions. Arrow, right? Because that was there. This is there. This is gone. This is gone. So the only thing left is H3PO4 as a liquid. Kind of makes sense too if you think about it, right? H3PO4 is because you have a plus 1, a plus 1, and a plus 1 ion for the hydrogens to balance out the negative 3 of the PO4. And there's only one of them, right? Well, there's one PO4 that's there, and the 3 hydrogens is there. And so this is the compound that is formed, phosphoric acid, when we end up taking these two things and putting them together. So the net ionic equation, what actually happens in the beaker, the reaction, is that. Now, let's do one that comes directly from your work. So. All right, net ionic equations. Let's do an example now right out of your packet. So number 1 says this. AgNO3. So silver nitrate, and it's aqueous. And sodium chloride, NaCl, likewise, aqueous. Yields AgCl solid and NaNO3. Well, the first thing we have to do, guys, is we have to make sure it's balanced. 1 silver, 1 silver. 1 NO3, 1 NO3. 1 Na, 1 Na, 1 Cl, 1 Cl. It's balanced. And by the way, this was also aqueous. That information has to be given to you to do a net ionic equation. So we said things that are dissolved in water, aqueous, are soluble. Okay? They can be broken apart. So what ends up happening here is this AgNO3 breaks down into 1 Ag plus 1 aqueous ion in the water plus 1 NO3 minus aqueous ion in the water. And now NaCl, it's aqueous, so it breaks apart into 1 Na plus 1 ion. Now, where am I getting these charges from? Well, when this compound is formed, right, the charges have to cancel. So that's where I'm getting these plus 1s and minus 1s from. Okay? So, and 1 Cl minus aqueous. Now, why am I breaking them apart? Because this is ionic equations. The ions, what do? AgCl solid, just that. It's a solid. It's not dissolved in water. It does not break down or dissociate is the term. So AgCl solid. Here, NaNO3, we end up with 1 Na plus aqueous ion and 1 NO3 minus aqueous ion. Next thing we do is we go look for spectators. What's on both sides but didn't actually do anything. So, 1 Na plus, 1 Na plus. 1 NO3 minus, 1 NO3 minus. Thus leaving me this. 1 Ag plus 1 aqueous ion plus 1 Cl minus aqueous ion, yielding AgCl solid. And that, my friends, is the net ionic equation. Let's do number 2. Number 2 says HCl aqueous, hydrochloric acid. It's dissolved in water, thank goodness, because that's some strong stuff, it's not dissolved. And zinc sulfide aqueous reacts to give hydrosulfuric acid in the form of a gas. Ooh, I want to be in the chamber. Plus ZnCl2 aqueous. What is the net ionic equation? Well, aqueous, so it breaks apart. Oh, by the way, I almost made a huge mistake. I almost forgot to balance. We needed 2 right here to give me 2 hydrogens for those 2 hydrogens. That also gives you 2 Cl's for the 2 Cl's right there. 1 Zn, 1 Zn, 1 S, 1 S. That would have been a drastic mistake. So what ends up happening here is this HCl is going to break down, right? Plus and minus. And this distributes. So what you end up with this is 2 H plus aqueous hydrogens and 2 Cl minus aqueous chloride ions. ZnS aqueous, therefore it will break down. There's a 1 right there, so therefore we have 1 Zn. Its charge is plus 2, so it gets a plus 2 because this is ionic equations. It's aqueous and 1 sulfur minus 2 aqueous ion yields H2S is a gas. It does not dissociate because it's just that, a gas. It has to be in water. It has to be aqueous to break down into pieces. Plus, this will break apart, though, into 1 Zn plus 2 aqueous ion. And this little 2 means you have 2 Cl's. 2 Cl minus aqueous ions, right? Gives you a -1 and a -1 to balance out the plus 2 here. So that plus 2 went there. And then the 1, 2 for the -1 Cl's. We look for spectator ions. So we say to ourselves, okay, 2 Cl minuses, 2 Cl minuses. 1 Zn aqueous, 1 Zn aqueous. Nothing else matches, so our net ionic equation is 2 H plus aqueous and 1 S -2 aqueous ion reacts to give H2S as a gas. Boom. Let me do one more. And it's a doozy, and it's number 8.